This talk in the Building Minds with Patterns series is about the deliberation pattern. We will briefly highlight the features of a generic cognitive architecture and discuss design patterns for cognitive systems. Then we will delve into the specifics of the deliberation pattern. And finally, we will show how this pattern fits into some existing cognitive systems. What is a cognitive architecture? A cognitive architecture is a design for an artificial mind. It is realized in a diagram depicting the elements of the mind that the architects claim are necessary and sufficient to support thinking or cognition. But how do we build such a system in the first place? The answer is simple. We need to establish a list of requirements identifying what the artificial mind will do. Once these requirements are elicited, we can then design a cognitive architecture to fulfill the requirements. So, at a very high level, some initial requirements could be that 1. We want an artificial mind to communicate with a device, such as a car, a robot, a smartphone, or an avatar. The device is situated in the real world or in a virtual world. 2. The device will send data, we can call this data observables, from the world to the mind and receive commands from the mind. We can call these commands actuations. 3. Some components will think about the observables and infer new information about them. We will call these coordination components. 4. We will need to have the system learn and improve its behavior over time. The system will therefore need to observe its own performance. We will call the components that reflect upon the system's behavior reflection components. 5. We want the system to stay within its capacity for memory and performance and not get slower over time. So we need periodically to consolidate the information stored in the system, and therefore we need components for that. These 5 basic requirements can be supported in many different architectures. We now present a generic cognitive architecture template. In essence, a cognitive architecture is a blueprint for an artificial mind. Here we see areas for observation, coordination, reflection, and consolidation, as well as the device situated in the world. In this template, we can see a device situated in a real or virtual world. This device communicates with a cognitive system through observation components, which store input from the device into the system's memory. The observation components are also responsible for communicating with the device's actuators, which perform actions in the world. We also see there are coordination components which update the memory with new inferences. The reflection components are responsible for changing the overall behavior of the system. And finally, the consolidation components are responsible for ensuring that the memory does not exceed its available capacity. What are cognitive system design patterns? Isaiah Berlin once said, "To understand is to perceive patterns." In building an artificial mind, it's helpful to start somewhere, and preferably not from scratch. There are a number of cognitive system design patterns which can be used to implement the required mind functionality. Mapping requirements to design patterns can assist in defining the overall mind architecture. Some design patterns are depicted here. This talk's focus will be the deliberation pattern. What is the deliberation pattern? Deliberation is problem solving. The deliberation pattern proposes actions to achieve objectives. Specialized problem solvers find viable event paths from situations to objectives. If there are no relevant existing paths, a problem solver will create one in the form of a complex action. Observables received by a perceiver are forwarded as situations to an action selector and concurrently to problem solvers. The action selector retrieves actions applicable to the current situation and relevant to the current objectives. This pattern is useful when the system is required to achieve or maintain objectives. The device with external sensors and internal monitors are situated in a real or virtual world. The observables contain percepts, urges, which are homeostatic deltas, and proprioceptions, which are the results of actuation attempts. The perceiver component updates the observables in memory. Using the most recent observables, the perceiver forms a current context or current situation in memory. Actions are formed from primitive actuations that the device can immediately execute. In addition to the primitive actuations, an action may be a policy, which has a set of preconditions necessary for the actuation to be executed. Or an action may be a macro operator, which contains both preconditions and expected effects. The macro operator may contain a chain of actuations or sub-macro operators needed for the successful execution of the macro operator. An objective is an identifier for a condition that the system wants to make true or attain. The solvers propose new actions for the current situation if an applicable or relevant action does not exist. The deliberator selects the most appropriate action which is both applicable to the current situation and relevant to the current objectives. The deliberator may be a coded system, rule-based system, or even a neural network. Each action should have a context which is matched against the current situation to determine the action's applicability. Each action should also have effects or results which can be matched against the prioritized objectives of the system in order to determine the action's relevance or utility. The deliberator prefers actions which are useful or relevant to the current objectives over actions which are simply applicable or reliable. Note that both applicability and relevance, or otherwise called utility, are factors the deliberator considers in selecting the next action. The executor is responsible for taking an action and sending the actuations to the device. An actuation is a command that the device can perform. Upon receiving an actuation, the device should send a proprioception indicating whether the action was performed back to the perceiver component. Forces for using the deliberation pattern include situations where the system is required to achieve or maintain objectives. What is a cognitive system? A cognitive system is a software and hardware implementation of a cognitive architecture. It is the instantiation of an artificial mind. There are a number of cognitive systems that have been researched extensively. Here is a chart of some cognitive systems and the design patterns they implement. Cognitive systems which have the deliberation pattern are highlighted in yellow with a red outline on the cognitive system chart. In order for us to study cognitive systems, we have to align them so that their elements are comparable. The characteristics among cognitive systems that seem important are the ability to perceive information from a device, the ability to be reminded of prior events and situations, the ability to create, retrieve, select, and execute actions. These general regions are depicted in the comparison template, and the cognitive systems we study will be laid out accordingly. The cognitive robotic system by Kawamura and Associates controls a robot using emotion and attention. The deliberator component leverages observables in the current situation formed by the event base, as well as emotional signals in the knowledge base to select actions for the executor to perform. Jan LeCun proposes an objective-driven cognitive architecture. This architecture partially matches the deliberation pattern, since the actor performs the executor function, and the configurator is expected to act as the solver. It is assumed that the world model contains the objectives, possible actions, as well as the observables of the current situation. The Manic Cognitive System by Gashler and Associates integrates learning and decision-making to model its environment and anticipate future beliefs, with the aim of achieving sentience through introspection. Manic models cognition with two primary components, learning and decision-making. The learning component is a recurrent model that learns to fit observed data in order to anticipate future observations. The decision-making component searches through the space of candidate actions to find actions leading to desirable future states. Manic combines three machine learning approaches: unsupervised learning, supervised learning, and reinforcement learning. Unsupervised methods reduce high-dimensional observations to form beliefs about its state. Supervised methods regress the outcomes of candidate actions. Reinforcement learning learns which states are desirable and chooses actions likely to lead to future desirable states. Manic's authors speculate that sentience may be achieved by leveraging introspective sensors. If outward-facing sensors enable it to understand and operate effectively in its outer environment, then it follows that inward-facing sensors should enable it to understand and respond to its own inner state. Since no empirical way to assess sentience is yet known, sentience in Manic cannot yet be evaluated. The transition model acts as the action selector for the forward model, and the planner serves as a dual purpose as the action selector and as the solver. Microsoft proposes an agent AI paradigm for supporting interactive multimodal generalist agent systems. In this case, the device represents an agent in the world. The device or agent has its own task planning capabilities. The system has components for task learning, memory, and action. Additionally, the cognition and consciousness component is used to appraise the current situation. With external training, the agent's actions can impact its ability to plan and perform its task. The agent may not require feedback from the environment to plan its next actions. This architecture only partially matches the deliberation pattern, since the executor and planner are not fully separated, and the device is also required to complete planning. The robotic control system, also called the NASREM system by Albus and Associates, is a real-time control system. RCS is implemented for the Multiple Autonomous Undersea Vehicle, or MUAV, Army Field Material Handling Robot, or FMR, and Army Team, Technology Enhancement for Autonomous Vehicles, Semi-Autonomous Land Vehicle projects. The sensors, modelers, and planners plan across increasing time spans, with components G1, M1, and H1 using the smallest time span, and components G6, M6, and H6 using the largest time span. The queuing network model of human processor system by Liu and Associates integrates two approaches to cognitive modeling: the queuing network approach, modeling parallel activities and complex structures, and the symbolic approach, which is strong at generating actions in particular task situations. It supports generation of real-time concurrent activities and separates perception, cognition, and motor processing into three continuous transmission subnetworks of servers, each performing distinct psychological functions. The Rogue system by Hai and Veloso integrates high-level planning, low-level robotic execution via the Xavier system, and learning in a mail delivery robot. The system leverages a classical planner, Prodigy, to create plans for multiple interacting goals. The robot monitors plan execution and replans as needed. So to recap, the deliberation pattern has a device that sends observables to the perceiver. The perceiver aggregates the recent observables into a situation, which is fed both to problem solvers and to a deliberator. Problem solvers propose new actions if none exist. The deliberator selects an action given the current situation and the objectives that exist. The executor transforms the action into actuations the device can perform, And finally, proprioceptive observables report the actuation's success. Forces for using the deliberation pattern include situations where the system is required to achieve or maintain objectives. You can read more about this design pattern in the book Building Minds with Patterns, available on Amazon. If you found this information useful, please like the video and subscribe to the channel, and visit us on Patreon. Become a member so that we can bring you more helpful content. Find us on the web at Linktree. If you need advice on systems you are building, book a consultation on Calendly. We'll see you in the next video.